Hi everyone. My talk at this meeting is about a new strategy for dynamic sampling from multi-modal distribution and calculating the partition function. I'm come from Institute of Applied Physics and Computational Mathematics, which is located in Beijing, China. This talk contains 5 sections. Section is about some necessary backgrounds of this job. Then I will give a brief introduction for some existing methods. In the third section, I will explain this new strategy in detail. Then some numerical results to show the validity of this strategy will be given in the fourth section. The last section is about some conclusions and perspectives. Of this talk is about sampling from the multimodal distribution and calculating the partition function. This problem is important, but it's hard because sampling methods tend to get trapped in local models of the density. In some situations, it is impossible to reach other models if no special treatment is adopted. The problem of sampling from the Gibbs-Boltzmann distribution. This kind of distribution is determined by a potential and a temperature. Sampling from this distribution is important in physics. It is clear when potential U has local minimums, F will be multimodal, which is a common situation. And calculating Z is also important and a challenge. Any Markov-Chain-Monte-Carlo method for sampling from this kind of distribution must face challenges of passing the high barriers to fulfill the condition of ergodicity. For the Monte Carlo method, a famous fact is the zero-variance importance sampling. When calculating an integral of a probability distribution function times a response function, sampling from the original probability distribution function may not be the best choice. You can sample from another biased probability distribution function, which is called the importance function, and use weight to get unbiased results. Theoretically, there exists an optimal importance function by which we can get a zero-variance result. That is mean one sample is enough, but it is unpractical because of the unknown integral in the expression of this zero-variance importance function. Even if we can sample from this probability distribution function, the unknown constant cannot be used as an estimate. These two problems will both be treated in the new strategy proposed in this job. If we treat the real variance importance function as Gibbs-Boltzmann distribution, Markov-Chain-Monte-Carlo can get samples of it symplectically. If the real variance importance function is a multimodal, sampling from it is also as a classical method. The Metropolis Hastings algorithm is widely used to sample from the Gibbs-Boltzmann distribution. Given current state xt, sample another state y from the proposal distribution. Then get a random number cosine. If cosine is smaller than the acceptance probability, y is accepted as a new state, or the particle will stay at xt again. Running these steps circularly for enough times, the state will obey the touched Gibbs-Boltzmann distribution. Note that when the proposal distribution satisfies Txy equals Tyx, the Metropolis Hastings method will be identical to the original Metropolis method. From above expression, it is clear that Metropolis Hastings algorithm is effective when applied to multimodal distribution if no special treatment is applied. Another general-purpose strategy to sample the Gibbs-Boltzmann distribution is the Langevin dynamical algorithm. From the diffusion theory, it is proved that the equilibrium distribution of the overdamped Langevin equation is a corresponding Gibbs-Boltzmann distribution. When simulating this distribution long enough, the states of the Brownian particle will obey the Gibbs-Boltzmann distribution. At any time t before the equilibrium state, the distribution of all particles' coordinates is called the transient probability density distribution. This concept will be used later in the new state proposed in this job. Generally, initial states which are close to the target distribution will be helpful to arrive at the target distribution rapidly. The Langevin equation can be simulated on the Euler scheme or the second-order Langevin algorithm. They are displayed in equation 2 and equation 3. Although the Langevin scheme can use bigger time steps to reach the target distribution rapidly, the Euler scheme has the benefit of using adjustable time step easily when the whole region is bounded. From the point of physics, when the barrier between two values is far more large than kb times t, the particle can hardly pass the barrier because of rapid attenuation of Gauss distribution. Existing methods for sampling from multi-modal distribution has evolved around two ideas. The first routine is using a timed version of the target density, such as simulated tumbling, evolutionary Monte Carlo, and simulated sintering. The second route is the state space is partitioned around the energy function and the density is properly reweighted in each partition, such as multi-canonical method, the entropy sampling method, the broad histogram method, and the Wang-Landau algorithm. Among these methods, the Wang-Landau algorithm is the most efficient one according to the present knowledge. It will be introduced briefly in the next slide. At the present stage, the Wang-Landau algorithm has been successfully applied to some complex sampling problems in physics. This algorithm is closely related to multi-canonical sampling. The main contribution of the Wang-Landau algorithm is in proposing an efficient method that simultaneously computes the balance weights and samples from the reweighted distribution. From the probability standpoint, the Wang-Landau algorithm is an example of adaptive Markov chain Monte Carlo. Now we will turn to the new stage for sampling from multi-modal distribution and calculating the partition function. We will use real-world variance importance sampling to illustrate the details. Calculating the partition function by probability density function reconstruction method. Optimizing the initial state to catch all the main regions of target distribution and modulating the transient probability density function to accelerate the formation of target distribution. We will illustrate these steps in detail in next slide. Suppose some perfect samples have been gotten and some probability density function reconstruction method has been used to estimate the real variance importance function at the point x star using these samples. Then the estimate according to equation 4 is the unbiased estimate of z when the number of samples tend to infinity. In this job, we focus on two probability density function reconstruction methods, that is, the histogram method and the kernel density estimate methods. For histogram method, in equation 5, mathematically, this is a low-order method to reconstruct the probability density function, and h is the only parameter of this method. When n tends to infinity, h can be smaller and smaller. When the probability density function has peaks, the histogram method may be more suitable to estimate the value of probability density function's peaks. For kernel density estimate method, like the expression in equation 6 and 7, it uses one-dimensional kernel function to reconstruct the original multidimensional distribution. Mathematically, this is the high-order method to reconstruct the probability density function, and HD in equation 7 is the estimated best bandwidth. When the probability density function is multimodal, this method may have some trouble in estimating the values of probability density function peaks, often underestimated. There are vast researches about improving the efficiency of this method. Now we will introduce optimizing the initial states. Divide the whole region into k subregions. Choose one subregion randomly and sample uniformly from this subregion m times. Noted x1 until to xm. Suppose this value is the largest one of all these values, and let xj is the final sample as an initial state. Repeat this procedure n times, then we get n initial states. Although these samples don't follow the target distribution, it can be assumed that the region with bigger distribution value will be sampled more frequently. The next step is to modulate the transient PDF. This step will be invoked after some Langevin simulation steps. Suppose after L steps, the states are x1L until to xnL. Let Wi is this value and Pi is this value. Now, the K is the estimation of this expression by probability density function reconstruction method. Using Pi to resample from these n samples, the final samples will follow the target distribution when n tends to infinity. This modulation will be run for some time, and after that, it can rely on Langevin simulation to reach the target distribution. The benefit of this step is to get samples more likely obeying the target distribution than the original one. There are two examples are used to illustrate the efficiency of the stretch. The first one is a two-dimensional integral, which has the essential difficulty of sampling from multi-modal distribution. Second one is a four-dimensional integral, which comes from particle transfer problem. We use form as an efficiency factor. Here, R is the relative error and C term is the computation term. Because the Wang-Landau algorithm is an art and there also exist some adjustable parameters in our stretch, it's hard to give fair rules for computation at the present stage. First some example is a two-dimensional multi-modal distribution like this expression. Apparently, the integral of this function is 1 and the zero-variance important function is itself. Because the distance of two peaks are far away enough and the value of equivalent potential is deep, it's harder for using Markov-Chain random walk to sample all the two important regions sufficiently. We will use this example to show two conclusions. The one is the stretch can get samples of a multi-modal distribution more efficiently. Another one is the realization of a real variance important sample using this stretch can get the unknown integration constant with high efficiency. In all cases, 10,000 particles and 500 steps are set. The time step is 0.001 and beta equals 0.1. For the new stretch, at the end of the 100th step and the 200th step, modulation will be invoked. Denote all samples x, xi, yi from 1 to 10,000. For the first conclusion, we start the particle in one way to mimic the situation of trapping the particle in local model. That is, the initial state is mu11, mu12, and the Brownian particle works randomly according to the Langevin equation without the modulation. Then the above-mentioned stretch is used to do the simulation again. Because the mean of all xi and yi is known, it can be used to compare the samples formed by these two methods. From this table, apparently the new stretch has sampled all the two important regions sufficiently. In practical situation for multi-modal distribution, only part of these models can be known in advance. So we use this importance function to do the importance sampling. We call it a simple importance sampling. To compare with the new stretch, and the sample number is 30 million. In the new stretch, the histogram method has been used to estimate the value of the probability density function with h equals 0.01. The efficiency factor form is used as a conversion standard. From the below table, it is clear that the new strategy has gotten better results than simple importance sampling. The second example comes from particle transporter problem. Suppose a fixed point source is located at 0, 0, 0, that is origin point. The source emits a neutron per unit time isotropically. The energy spectrum is a Maxwell spectrum, as shown by this expression. A superior shear whose center is origin point is around the point source. The inner radius is 1.5 and the outer radius is 1. This shear is full of pure absorbed matter whose macro absorbed cross-section is sigma e, as illustrated as this expression. If the total flux in this shell is a target, then F equals this expression. We use a Monte Carlo particle transport simulation to get the benchmark answer with 100 million particles, and the answer is this number. The red number is the relative error. Then the new strategy is utilized to get the integral again, using 20,000 samples and 300 Langevin steps in total. In the calculation, the Euler scheme with adjustable time step is adopted to avoid penetrating the boundary. The inner states are the optimized one as suggested in last section. The real valence importance functions are estimated at the first 10,000 final states using the whole 20,000 final samples by kernel density estimate. Because this problem is not a multi-modal, the modulation step has been omitted. In this table, direct Monte Carlo means we use samples of Fe and uniform samples from the shell to do the integral. From this table, we can conclude that the new strategy is much more efficient than the direct Monte Carlo integral. Now is the conclusions and the perspectives. The strategy proposed in this work contains two main steps. The first is using optimization of initial states and modulation of transient probability density function to sample from multi-modal distribution. The second is using probability density function reconstruction method to calculate the partition function. This strategy is efficient as a general purpose one. At the present stage, this strategy is an art in some degree. So we need more workers to transform the art to the science. Thanks for your attention.